Okay, class. Sorry, my internet went out and gave it a few minutes. It's not coming back on at the moment. So I'm just going to record this and then I'll post it. And if there's any questions, we can go over that on Monday. So we're just talking about the purpose of a transformer and that it can convert voltages. And there's two reasons why that's so useful. We have a standard outlet, which in America, 120 volt RMS. And what if you plug a device into the outlet that doesn't want 120 volts? Like every device has its own needs. And so, you just use a transformer to convert that 120 volts to whatever voltage the device needs. Now that transformer would typically be built into the device. So that's one application of a transformer, but that's a very important one. There's nothing like this in DC where you can just convert voltages like this. Now another important application is power transmission, where it's more efficient to transmit power at high voltage. So we produce energy at a power plant, but then we have to deliver it for miles to get to your house or wherever it's going to go. And so, we know that the losses due to this joule heating, that I squared R, that's kind of minimal in a lot of applications. But when you're transmitting a lot of energy over a large distance, that can become significant. And so we use a sequence of transformers in the energy grid. So the first thing they do after the power plant, they use what's called a step-up transformer to increase the voltage to a very high value, like hundreds of thousands of volts. And those are those suspended cables that you see. So those are extremely high voltage, which is efficient, but also very dangerous. And then, you get that to your neighborhood, for example, and you don't want hundreds of thousands of volts being delivered to your house. And so then there's a sequence of step-down transformers that lower the voltages to safe levels, ultimately getting 120 volts to your house. Now, our power grid is actually a bit more complicated than that because we have different lines going to your house that are all like 120 volts, but they're all kind of offset from each other. So we described how they're described by a sine function, but we have different lines that are offset by 120 degrees. And the reason why is you can combine them in different ways to get, like, say, 120 volts or 240. And you might have some outlets in your house that are at 240 volts. Like maybe in the kitchen or like a laundry room. For big appliances like refrigerators or something, they might require a higher voltage. But we're just kind of sticking to the basics here. So anyways, transformers, very useful for, they can very easily convert voltages from one value to another. And the current in the primary and secondary coils are related as well. I'm going to write that down. And again, we're making some simplifying assumptions here. What we're assuming is that there's no current lost due to like resistance in the wires. Usually a pretty good, so we're assuming that whatever power we're delivering from this side, that's being transmitted to this side. Not 100% accurate, but if we make that assumption, remember power is current times voltage. So if we just cross multiply here, we see ES times IS equals EP times IP. So that means that the power in the primary and the secondary are equal. So we have this inverse relation for the transformer. Okay. ask any questions right now. So I'll do a few suggested problems, and then if you have any other questions, then we can talk about that in class on Monday. Let's see if the internet's back on yet. Yeah, still don't have internet. Alright, let me look at, there's only, if we just do induction and transformers today, there's only 5 problems. I think I'll just do those. Okay, so one, it says a solenoid that is 1.26 meters long formed from 1,870 windings. So you get a solenoid like this, and then just wrap it around, probably more than I've got here. Carries a current .36 amps. The radius is 2.78 centimeters. So the question is, what is the inductance of the solenoid? That's one we can figure it out, worked it out in the notes. But let's just look at the equation sheet to see if it's on there. I do not believe that it is. Alright, let me I'm just going to write down the inductance and then we will calculate it. Yeah, so the inductance in a solenoid, mu naught little n squared L A. So that's the inductance in a solenoid. So let's calculate this. So mu naught, I'm going to write that as 4 pi times 10 to the minus 7 Tesla meters per amp. Now, n is little n is big N over L. So here we have n squared L. So we'd have big N squared over little n squared times L. So this is going to be n squared divided by the length. So we have 1,870 squared divided by 1.26 meters. So that covers the little n squared L. Now the area is pi r squared. I should have used a 1.26. I knew there was going to be a pi involved in this one as well, but not in a way that cancels out. But anyways, and convert this to meters, and then square it. So we want to get henries out of this. So a henry times an amp is a volt times a second. We want to get rid of these Teslas as well. Let's see. I know I need that Henry amp as a volt times a second. What else do we need? A Newton times a second is a Coulomb meter times a Tesla, except we want to do that the other way. A Newton times a second Coulomb meter times Tesla. I'm going to write it like this. But now we've got newtons. Do we have volts anywhere? Yeah, we do. Okay. So a newton times, let's look at a joule is equal to a coulomb times a volt. So actually I'm going to go back to that. So that's a conversion factor in the equation sheet. Leave it there. And then a joule is a newton times a meter is a coulomb times a volt. So let's see if this works out. We have Tesla times meters squared, Henry, amp, Newton, second, coulombs, and volts. At the bottom we have amps, meters, volts, seconds, coulomb, meters and Teslas, and then newtons and meters. So we actually do get henries out of this. So let's collect all the numbers now. So we have 4 pi squared times 1870 squared. I'm actually going to write it like this. Just thinking of how we'll do this in the calculator. So we can do 1870 pi, square it, and then multiply by pi. So that takes care of up to here. 2.78 squared. We could have thrown that in the parentheses as well. On the bottom, we have 1.26. And then this is 10 to the 4, so 10 to the 11th. So let's do this. So I'm going to do 1870 times pi. I'll do 2.78 as well. So I'm getting is, 16,332. And then I'm just going to square that. And multiply by 4. Divide by 1.26. So what I'm getting is 8.47 times 10 to the 8th. But then we're dividing by 10 to the 11. So I'm getting 8.47 millihenries. So yeah, even with a solenoid, which is, kind of like an ideal device for producing inductance, we're still in the millihenry range. This is a fairly large solenoid as well. It's over 1 meter long. The radius, the diameter would be a couple inches. So it's not a small thing at all. So we're still in the millihenry range. Yeah, in the notes I get 8.49 millihenries. Close enough. Okay, so that was problem 1, just calculating the inductance of a solenoid. Let's look at problems 2 and 3. So suppose you wish to make a solenoid whose inductance is 1.4 millihenries. The inductor is to have a cross-section area of 1.2 times 10 to the minus 3 meters squared and a length of 5.2 centimeters. How many turns are needed? So let's write down the inductance. So we've got mu naught. Now I'm going to replace lowercase n with capital N. So we'd have big N squared over L squared, but then times L. And then we have the area. So we're trying to solve for N. So I'm using lowercase l for length of the solenoid because uppercase L is the inductance. So let's see, we have inductance times length over mu naught times the area. So we have 1.4 millihenries. The length, 5.2 centimeters. Mu naught, I'll just do the 1.26 over 10 to the 6. And A is 1.2 times 10 to the minus 3 meters squared. So now we need our conversion factors. A Henry times an amp is a volt times a second. We want to get all these units that cancel out, actually. We want to get rid of Teslas. So a Newton times a second is a Coulomb meter Tesla. And a Newton times a meter is a Coulomb times a volt. So same conversion factors we used last time. Let's just check. Henry times meters times amp, volt second, Coulomb meters Tesla, and Newton times meters. On the bottom we have Tesla, meter, meter squared, Henrys, amps, newtons, seconds, coulombs, and volts. And everything cancels out. So, yeah, we're getting a number squared, which is dimensionless. So let's see how many windings we would need. So let's see, 1.4, 5.2 times 10 to the 9th divided by 1.26. 1.2 times 10 to the 5th power. So I'm just going to multiply the numbers. 1.4 times 5.2. And then dividing, I divided by 1.26 and hit enter. And then I'll divide by 1.2 again. You have to be careful, just order of operation thing. So I'm getting here is 4.8 times 10 to the 4th power. And so now taking the square root, I'll just take the square root of 4.8 and multiply by 100. Square root of 10 to the 4th is 100. So, so I'm getting around 219 turns. And let's check the enter key. 220, good enough. Let's round it off. Okay, so that was problem 2. So let's look at problem 3. So 2 coils of wire are placed close together. There's initially a current of 2.5 amps. I'm going to call that the primary. But there's no current in the other. So the current is then switched off in a time of 3.7. Times 10 to the minus 2 seconds. Now the average EMF induced in the other coil, so that'd be the secondary coil, is 1.7 volts, what is the mutual induction of the system? So we have one coil here carrying a current, and another coil here that doesn't have anything going on. But again, there's a magnetic field due to the primary coil, which is producing a flux in the secondary. So if we cut off this current, the flux here disappears as well, and that will produce a current in the secondary one. Well, there's an EMF in the secondary. So, and again, this is just applying this formula. Let's just solve for M. We'd have the EMF in the secondary coil times that time interval divided by the change in current in the primary coil. So that's just the initial primary coil, because the change, it's going to go to 0. So here we have 1.7 volts divided by 2.5 amps times 3.7 times 10 to the minus 2 seconds. And we want henries out of this. So a henry times an amp is a volt times a second. And this will give us henries. The amps cancel out, volts, seconds, we get henries. Just going to calculate this. 1.7 times 3.7 divided by 250. I'm going to convert to millihenries, getting about 25 millihenries. So that would be the mutual induction in these two coils. Which is also what I got in the answer key. Okay, so now there's two questions with transformers. So let's just do that and call it a day. We'll talk about energy and B fields. Maybe I'll briefly talk about it, but yeah, then we'll see if there's any questions on Monday. So transformer problems. Here the secondary coil of a step-up transformer provides a voltage that operates an electrostatic air filter. Now, symbolically, we can represent a transformer like this. So like here's the primary coil, here's the secondary coil. So it's a step-up transformer. So if we have 120 volts here, we're going to have more, it ups the voltage. The turns ratio is 50 to 1. Let's say I call that R. So, again, there's like a definition for turns ratio, like NS over NP or NP over NS. I don't really worry about memorizing that. I know it's a step-up transformer, so we're going to up the voltage. So the primary coil is plugged into 120 volts. So yeah, it's a step-up transformer. So we're going to have 6,000 volts in the secondary coil. It's a 50 to 1 ratio. 50 times 120 is 6,000. The current in the secondary coil is 1.7 milliamps. Find the power consumed by the air filter. So power is current times voltage. So we'd have 1.7 milliamps times the voltage. So this 1,000, we have 1.7 times 6. So that would be 10.2 And an amp times a volt is a watt. So let me just check. Yeah, 10.2 watts. Yeah, so usually I try to be clear. Like in this problem, I worded it so it's a step up transformer. So you know the voltage in the secondary coil is higher than the primary by that turns ratio. Okay, so one more transformer problem. So in a television set, the power needed to operate the picture tube comes from the secondary of a transformer. So very similar. The primary is connected to a 120 volt power supply. The picture tube uses 91 watts. I'm just going to write power is 91 watts. Not power in the secondary coil, because in our idealized version of things, the power will be the same in both coils. So there's 5.5 milliamps in the secondary coil. We want to find the ratio of the transformer. So what we want to find specifically is NS over NP. Okay. So let's see. Power is 91 watts. We can use that to find the voltage here. So the voltage in the secondary coil would be power, which is 91 watts, divided by 5.5 milliamps. So let's multiply by 1,000. And yeah, watt is an amp times a volt. So we will get volts out of this. The watts cancel and amps cancel. So let's do 91 divided by 5.5 is 16.55, and then times 1,000. So that's 15.6 kilovolts. So this is definitely a step up transformer. And so what we have is EMF in the primary, EMF in the secondary. So now that we have those, the number of coils in the secondary over the number of in the primary is the EMF in the secondary over the EMF in the primary. So that would be 15, I'm just going to say 15.6 times 10 to the third divided by 120. Or 156 over 120 times 100. So 156 divided by 120, 1.3. So 130. So if you had, say, 10 loops here, you'd have to have 1,300 here. Now, I don't know. There's probably engineering. Why don't you just go with like 1 and 130, or 10, 1,300. They have the same turns ratio. There's additional factors. I'm sure we would like if you were actually going to design a transformer. Other things you might want to take into account. And I did this wrong, I believe, in the answer key. I had the ratio. I did like 120 over. Yeah, so ignore the answer key. This should be. Let's check the number. That was a little off too. Okay, I got the number wrong in this one, but the ratio wrong in the other one. So it should be about 138. That's what I got in the answer key, except I wrote 1 over 138 instead of just 138. It's a step-up transformer, so we should have more turns in the secondary coil. So just ignore the answer key on that one. I'm going to make a note of that as well. Okay. Now, also on the schedule today was energy and magnetic fields. I'm not going to do the suggested problems, but let's look at that solenoid. Actually, let me, we found the inductance for a solenoid. Well, it's in the notes, but the energy, like if we start out with the solenoid, and there's no current, let's say we apply a current, so we have to apply a voltage, and then we can turn on a current, but the solenoid is going to fight us, because when we establish a current, there's going to be a back EMF. And so, in order to build up a current, or say we already have a current, if we want to increase the current, the solenoid is going to respond with this back EMF. And so, to build up a current, we're going to have to put some energy into it. And we interpret that energy as being stored in the solenoid itself. And the energy, I'm going to write out the word energy, so probably not likely to mistake it for electric field, but in some cases we could. So, 1/2 Li squared would be the total energy that it takes to build up a current in a solenoid, and we interpret that energy as being stored in the solenoid. And the solenoid occupies a certain volume, which is basically just its length times that cross-section area of the coils. So I worked out the details, but the energy density so we use the letter U for energy density. It's B squared over 2 mu naught. Now, we're going to kind of just move on from here. This is kind of like a specific problem. How much energy would it take to establish this current in a particular device? But this result turns out to be rather important. Because we interpret the energy as being stored in the magnetic field, just like when we charged up a capacitor. Like all the electric field, it's pretty much between the plates of the capacitor, maybe a little bit leaks out. But we consider an idealized capacitor, where it's like the electric fields only exist between those two plates, and it takes energy to charge up the capacitors. We can interpret that as being stored in the electric field of the capacitor. But the result is much more general, that these electric and magnetic fields do store energy. So in the case of electric fields, the energy density was 1/2 epsilon naught E squared. For magnetic fields, we have 1 over 2 mu naught times B squared. In both cases, the energy density is proportional to the field squared. And the main we don't really do much with it now, but actually the next topic though, we're going to talk about electromagnetic waves, which of course consist of both electric and magnetic fields. and a very important property of waves is they carry energy. So this will be a very important topic for what we're going to do later. But yeah, that'll be it for today. So sorry, my internet cut out, and as far as I know, it's still gone. Yeah, internet is not working for me right now. So I'll upload this when I can. And yeah, if you have any questions on any of this stuff, we can talk about that on Monday.